Hello. Since I'm not in school today, I've decided to make a video that will introduce the topics of the day that we would have covered during class. Um, so, the topic of the day is to understanding the quantum mechanical model. And to start with, I want to recap models of the atom. So, according to Rutherford, you can see there is a nucleus, and there are electrons that are separate from the nucleus, but those electrons are just sort of kind of randomly positioned, spinning around the nucleus. Um, Niels Bohr, in work that we studied before the winter break, um, he was able to delve a little bit deeper, and he realized that electrons are not all the same. Electrons can exist in certain specific energy levels. Now, we primarily studied the hydrogen atom, and hydrogen only has one electron. Um, so we could see that electron in the ground state in the first shell, but it would potentially be able to climb to a different shell if it is excited. Now, Bohr's model also applied to other atoms. So, for example, here's magnesium, which has 12 electrons. According to Bohr, two electrons can exist in the first shell, and then eight in the second, and then the third would contain the remaining two electrons that magnesium has. So, whereas Rutherford seemed to just think that the electrons were outside um, outside the nucleus, Bohr was able to characterize this a little bit further, that there are certain numbers of electrons that can exist in certain energy levels. And of course, not all electrons are the same because some are at lower energy levels and then some are at higher and higher still. Now, there were issues with Bohr's model, and some of those we started to address yesterday. There were certain phenomena that we learned about how, for example, electrons they really behave as waves, and they have wave functions. They are not simply spinning around the nucleus in a very predictable orbit. So there were a number of scientists that put together the quantum mechanical model, and essentially uh, they realized that it's not just that there's a first shell, a second shell, and a third shell, and so on. There are subshells. So if we look, here's our first level, and then our second level actually contains what is called the 2s and the 2p. So the first shell has just the 1s, but the second shell has the 2s and the 2p. The third shell contains the 3s, the 3p, and the 3d. And the fourth shell contains the 4s, 4p, 4d, and eventually the 4f. Um, Now, you might be wondering about these S, P, D, F, what they mean. These are essentially shapes of what are called orbitals that can hold electrons. So, if we look at this right here, the 1s is showing basically a cloud of probability where there's a good chance that you'll find an electron that is occupying the 1s orbital. The 2s orbital, you can see, is similar in shape, as is the 3s. All of the s orbitals are similar in shape, but in the third energy level, the orbital is bigger. In the second energy level, it's smaller. In the first energy level, it's smaller still. There also are p orbitals, and notice that each shell contains up to three p orbitals, px, py, and pz. They're just different orientations. Um, and we can see the same thing with the 3p x, the 3py, and the 3pz. They're similar in shape, just a little bit bigger than the 2px, 2py, and 2pz. So, um, how does this play out? Well, remember that according to the Bohr model, and this is something that you may have seen in middle school, two electrons can fit in the first shell. Well, in the first shell, according to the quantum mechanical model, there is only one orbital, and that one orbital can fit the two electrons. Notice that in the second shell, according to the Bohr model, there can be 8 electrons. And if we look at the quantum mechanical model, there are 1, 2, 3, 4 orbitals that can each hold 2 electrons, giving us 8. So Bohr's model was correct to an extent. It was correct in predicting the number of electrons that can fit in a shell. It's just that Bohr didn't really know about the concept of subshells, that the second shell can have electrons in two different types of what are called subshells, the S and the P, for example. So moving back here, um, we can see the relative energy of orbitals. So in the first shell, we've only got the 1s, and this 1s can hold 2 electrons. And notice there's only one orbital here. So the s always contains one orbital. And you'll notice that that's the case in all shells. The 1s, the 2s, the 3s, the 4s, they all have just one orbital shown. But when we look at the p's, well, the 2p, 3p, 4p, 5p, 6p, they all contain 3 orbitals, which hold a total of 6 electrons. As for the Ds, they all contain 5 orbitals, and the Fs contain 7 orbitals. You can count them: 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. Now, those, as I mentioned, those orbitals, they are populated by electrons. And so if, for example, um, we have an atom with, say, 12 electrons like magnesium, well, the first 2 electrons go into the 1s, and they are signified by these arrows up and down. So that's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what we've done is we've just filled in order the first several orbitals, starting from the lowest energy and going up. And what we find is that magnesium, with its 12 electrons, has electrons in the 1s, the 2s, 6 electrons in the 2p, and 2 more in the 3s. Now, the periodic table is actually organized in a way to make it easier to tell electron configuration, to tell sort of how electrons are distributed in an atom. Remember, I said magnesium. Uh, so the highest energy electron was in a 3s orbital. Well, magnesium being element number 12, it's actually right here. And I'll put a little mg here. So actually, notice that it is in the S block, right? These first 2 groups are called the S block, and it is in the third row. So it's the 3s, and it's the second one over. So actually, 2 electrons being in the 3s orbital would be that would be the highest energy electron pair in the magnesium atom. So, for example, if we were to look over here, this would be boron. Well, boron, it's the first element in the 2p area. This is the p block. This row is the second row. And so in the 2p, the first element is boron. So we would expect its highest energy electron to be in the 2p, and it would be just with one 2p electron there. So um, we'll fill in some electron configurations a little bit later. I do want to point out that the periodic table actually should look like this, but it's a little bit too broad to comfortably print. So actually, these guys are pulled out usually, and the S and the D blocks are put together. But the periodic table is organized according to the building up of electrons. I'll get into noble gas configurations at another time. There are 3 rules for filling orbitals, and they're the Aufbau principle, the Pauli exclusion principle, and Hund's rule. I'm actually going to skip over this because I cover that in a YVO. That's your homework for tonight. So just excuse me here. All right. So what I'm going to do is I'm going to fill in what is called an orbital diagram. Orbital diagram. And we're going to do the orbital diagram of, let's go with phosphorus. So phosphorus, if you look it up in the periodic table, it's element number 15. And having 15 electrons, they get filled in as follows. One goes in the 1s, and a second one goes into the 1s. After that, the next highest energy is the 2s. And then we have the 2p. Whoops. Sorry about this. There should be 6 in the 2p, 2 in the 2s, and 2 in the 1s. Then we have 2 more in the 3s. And if you're keeping track, we're at 12. The remaining 3 go into the 3p as follows. So this would be an orbital diagram for phosphorus. Notice we start from the lowest energy and go up. Also notice that we put 1 electron into each orbital of the same energy before pairing any. So it's this with each orbital occupied rather than having it like this. I'm going to go back to what's correct here. Also notice that every orbital has an electron with an up arrow and a down arrow. If they were both up, they would be the same thing, which doesn't make any sense. So that's an orbital diagram. And what we're going to do is we are going to take this and we are going to relate this to what is called electron configuration. Sorry about this. So electron configuration is just another way of describing how electrons are in the atom. So if we look here, we've got electrons in the 1s. So our first thing to do is to write 1s. And the fact that there are 2 electrons in it means that we're going to put a 2 here. It looks like an exponent. It doesn't mean that you're squaring anything. It's just the way the symbol is written. After the 1s comes the 2s, the next one up. And it holds 2 electrons. Beyond that, there's the 2p. And the 2p, since there are 3 orbitals, you can see it's holding 6 electrons. Then we have 3s holding 2 electrons. And then we have 3p, which could hold up to 6, but in the case of phosphorus, it only is holding 3. And if you count these up, that 3 here, the 2 here, the 6, the 2, and the 2, combined, they give you the 15 electrons that you're expecting phosphorus to have. So this is called an electron configuration. This is called an orbital diagram. And those are the 2 important things to take from today's lesson. I will, excuse me, I will draw one more, and let's go with titanium. So titanium, which contains 22 electrons that you could get from the periodic table. Sorry, that should be up, down. So I'm just drawing out the orbital diagram. So there we go. This is titanium. Titanium's orbital diagram. Now, if you would like to write out an electron configuration, the electron configuration of titanium is as follows: 1s2, 2s2, 2p6, 3s2, 3p6. And notice, actually, after the 3p, the next highest energy level is the 4s. It comes before the 3d. They're close, but 4s is actually a little bit lower in energy than 3d. So 3d is the last thing, and that contains 2 electrons. And so that would be your electron configuration of titanium. Do want to go back to the periodic table just briefly. So notice 1s comes first, and then 2s, and then 2p, and then 3s, and then 3p, and then 4s. And then when we finally get to the D block, note that although it might be in the fourth period here, next to the 4s and the 4p, but when we're in the D block, it lags behind by 1. So this is the 3D, not the 4D. The 3D is the first D row, if you will. The 4D is the next one, then the 5D, and then the 6D. And you just need to remember that when we're talking about the S and the P blocks, the number of them is equal to the period number. This is period 1, period 2, period 3, period 4. Oops. Period 1, the S block is the 1S. Period 2, the S block and P blocks are the 2S and the 2P, etc., etc. But when we get down to period 4, yes, the S and the P blocks are 4, but the D block, we're talking third energy level. Similarly, the F block, which actually should be inserted here, the 6S comes before the 4F, and then the 7S comes before the 5F. And actually, after the 4F comes 5D, and after the 5F comes 6D. We'll talk about this more tomorrow. One last thing. When you're drawing an electron configuration, you can use the periodic table to help you out. So for example, if I were to do silicon right here, excuse me, silicon, it has 14 electrons, and basically we are just going to read the periodic table left to right, top to bottom. The first thing is the 1s, and the 1s is filled with 2 electrons. After the 1s comes the 2s, and it is filled with 2 electrons. After the 2s comes the 2p, and it is filled with 6 electrons. We're just reading the periodic table here. After the 2p comes the 3s, and it is filled with 2 electrons. Note this is silicon. Silicon's electron configuration. All right, finally, we go to the 3p. Silicon is in the 3p, so we shouldn't just necessarily go, oh, 3p6, because it's a p, right? P can hold 6. Actually, it's the second one over in the 3p. So that means that it has 2 electrons in the 3p. And so, well, here we go, 3p2. So that would be the electron configuration of silicon. And you could just basically do this continually. Just if you got any element, you could just pick out, oh, it's, here, this is zinc. So zinc is in the 3D, and it's the 10th over. So you would basically just build up until 3d10 for zinc. And you'd have to know 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and the last term would be 3d10. We will cover this more in class tomorrow, but hope this video has been helpful. Feel free to reach out if you have any questions or comments. Thank you.